Okay, hello everybody. Welcome to our 6.2 concept video. And in this part, now that we've learned about multivariable functions from 6.1, now we get to explore, well, how does calculus work with multivariable functions? Specifically, how do derivatives work? How do I take a derivative of a multivariable function? Well, what's going to help us understand this is, first off, just remembering what a derivative is. A derivative is an instantaneous rate of change at a specific x value, or independent variable. But if I dive into this even more, what is a rate of change? Rate of change is, right, how does your y change as your x change? Or how does the dependent variable change as the independent variable changes? That's what a rate of change is. And so we run into our hurdle here with multivariable functions is, what do I do if I have multiple independent variables? I don't just have one anymore. How does this work if I have multiple things that are changing? Well, the bottom line here is we're going to focus on one variable at a time. So if I have some multivariable function, we're going to focus on a function with just two independent variables. Then what I can do is I can just take the derivative of this function just in terms of one of my variables, one of my independent variables. I'm just going to focus on one at a time. And this is what's called a partial derivative. And I have interesting notation for that. You remember with Leibniz notation before with normal derivatives, it was this d over dx. With partial derivatives, we use this fancy d. So I'll say dz over dx, but with this fancy d. And the other notation I have it is this f sub x. And what does this mean? This means I'm taking the derivative specifically in terms of x. I'm focusing on x. Which means that I can also do the same thing in terms of y. I can take the partial of z, the partial derivative of z, in terms of y. Notice how I'm changing that denominator because now I'm taking the derivative in terms of y. And similarly, my function notation would just switch to f sub y of xy. And that would mean that I'm taking the derivative in terms of y. And I'd really be asking myself the question, how does z change as y changes? So that's really the big idea with partial derivatives. But how does this work in practice? How do I take a derivative in terms of x that also includes an independent variable y? Well, the way we do it is, if we're taking the derivative in terms of x, we're assuming x is changing. But if we're focusing on x, then we're going to assume that y is not changing. So the big idea with my partial in terms of x is we're going to treat y, or really all other independent variables, as a constant. We're going to treat y as if it's not changing, if it's just some constant value. And then on the other side, right, if we're taking the partial derivative in terms of y, we're going to treat x as a constant, or really any other independent variable. We're going to treat all the other independent variables as constant, as if they're not changing. What that means is if I'm taking the partial in terms of y, and let's say I've got some term that's just in terms of x, and I took the derivative of this in terms of y, well, that's not changing. It's not changing because x isn't changing. We're assuming that x is staying the same. Only y is changing in this scenario. And since x isn't changing, we're treating it as constant. What's the derivative here? This derivative would just be equal to 0, even though it contains a variable. Why? Because we're treating x as a constant. So that's how these partial derivatives work. We're going to take the derivative in terms of one variable, treating everything else as constant, treating as if it's staying the same. So let me ask you this question. How would my interpretation change if I actually plug numbers in for my x and y? Well, the way I could interpret this is, how does my output change when y, or my y variable, is fixed at some value b? So y isn't changing, it's fixed, it's a fixed value. And x changes from a, right? A represents what the x value is now, to a plus 1, right? I'm just increasing x by 1 and seeing what that does to my output value. So that's what this partial derivative actually means with values plugged in. But now let's talk about second order derivatives. Remember, a second order derivative is really just taking the derivative of a derivative. But how does that work when I'm working with partial derivatives? Well, notice how if I have a multivariable function with two independent variables, then how many partial derivatives do I have? I have two different partial derivatives, a partial derivative in terms of x and a partial derivative in terms of y. So if I think about taking the derivative again, taking partial derivatives again, that means I have four different possible second order derivatives. How? Well, I could take my partial derivative in terms of x and take the derivative in terms of x again, giving me this f sub xx, meaning I've taken the derivative in terms of x two different times. But my other option is I could take the partial derivative in terms of x and then take that derivative in terms of y, giving me the partial derivative in terms of x and then y, f sub xy. Well, on the other side, I could take my partial derivative in terms of y and then take that in terms of x. Do you see the difference between those two? Even though they both involve this xy, the first one means I took the derivative in terms of x first and then took the derivative in terms of y, while the second one is I took the derivative in terms of y first and then took the derivative in terms of x. And then, of course, my fourth option is just taking the derivative in terms of y twice. So four different second-order derivatives for a function with two separate independent variables. And that's how second-order derivatives work with multivariable functions. So go ahead and start on the homework, see what you can do, try out these derivatives with these multivariable functions. And if you get stuck, check out the examples video. Good luck, you guys.